Welcome to the solutions to the Thermodynamics Problem Set, problems numbers 1, 2, 3, and 4. Let's hop right in with number 1 here. We have a cylinder with a movable piston. Contains a gas at a temperature of 27 degrees Celsius. That's its initial temperature. A volume of 1.50 meters cubed, its initial volume, and a pressure of 0.2 times 10 to the 5th pascals, its initial pressure. What will be its final temperature, T, if the gas is compressed to 0.70 meters cubed, V, and the absolute pressure increases to 0.8 times 10 to the 5th pascals, its final pressure. It should be obvious that what we're doing here is comparing a gas in some initial state to that same gas in some final state. This allows us to use the ratio or the equation, the ideal gas equation, POVO over TO equals PV over T. We go ahead and we make our substitutions. Our pressure and volume was both given in standard units, so we can directly substitute there. However, we have to pay attention to our temperature in this problem, as it was given in degrees Celsius and needs to be in degrees Kelvin. Whenever using the ideal gas equation, temperature has to be in Kelvin because the gas law constant has units of Kelvin in it. We go ahead and substitute and we solve for T. Pause the video if you need a moment to do so and check your answer that T is 560 Kelvin. All right, on to number 2. What is the average kinetic energy, kAV, of a molecule of oxygen at a temperature of 300 degrees Kelvin? We go to the reference table for help on this one, and we understand that these two are directly proportional. Temperature is a measure of the average kinetic energy of molecules, but we go to the reference table to find the equation that relates the two, and it's K average equals 3 halves kBT, where kB is Boltzmann's constant. We go ahead and we substitute 3 halves 1.38 times 10 to the -23 joules per Kelvin. And this, of course, tells us that because of Boltzmann's constant, our temperature has to be in Kelvin. It's given in Kelvin, so we go ahead and directly substitute. Kelvin cancels, and when we calculate, we should get 6.21 times 10 to the -21 joules. Okay, pretty easy, straightforward, but what were you supposed to learn from doing number 2? That temperature is a measure of the average kinetic energy of the molecules of a gas. It's actually the average kinetic energy of the molecules of any substance, but in this unit we'll talk about gases. Number 3, we have 3 moles of nitrogen gas at 27 degrees Celsius. So 3 moles is little n. We have our temperature at 27 degrees Celsius contained in a 22.4 liter cylinder. That's its volume. They want us to find the pressure of the gas that it exerts on the cylinder walls. The issue in this problem is that our volume is given in units of liters, and we need it to be in standard units of meters cubed. So this is a one-time dimensional analysis calculation that is being shown to you. From now on, we'll just substitute, if we're given liters, times 10 to the -3 at the end of that to convert to meters cubed. But showing you where that comes from, we're going to do this dimensional analysis calculation here. We have 1 liter, and we need to get rid of liters and convert over to distance cubed units, this specifically meters cubed. So in this case, we make the connection that a liter, 10 to the -3 liters is 1 milliliter. This cancels our liters units. In the conversion that gets us from volume units to distance cubed units is the fact that 1 centimeter cubed is 1 milliliter. In fact, That's how the milliliter was invented. Was they took a box that was a cubic centimeter in size, filled it with water, and said that that's going to be called a milliliter. That's why in hospitals a cc is the same thing as a milliliter, cubic centimeter. All right, so that cancels our milliliter units, and now we got to get from cubic centimeters to cubic meters. Our conversion here is 10 to the negative 2 meters in 1 centimeter. We're going to cube that to get meters cubed units. When we do that, we also get centimeter cubed units. 1 cubed is 1. Centimeter cubed is centimeters cubed. This, of course, cancels these units, which is what we're looking for. And 10 to the negative 2 cubed becomes 10 to the negative 6. We've cubed, so we can get rid of our 3 there. And what's left, we have our desired meter cubed unit. From a mathematical analysis here, we have 1 times 1 times 1 times 10 to the negative 6. So that gives us 10 to the negative 6 in the numerator. We have 10 to the negative 3 and a 1 and a 1 in the denominator. That gives us a 10 to the negative 3 in the denominator. 10 to the negative 6 divided by 10 to the negative 3 is 10 to the negative 3 meters cubed. Like I said, from now on, we won't go through all of that. We're using the ideal gas law equation here, PV equals nRT. We go ahead and we substitute P times 22.4 and just add the times 10 to the negative 3 on the end to get your meters cubed, equals 3 moles times 8.31 for the gas constant. And our temperature also needs to be in Kelvin, 27 plus 273. Go ahead and calculate, solve for P, the pressure, and we get 3.34 times 10 to the 5th pascals. Our last problem, problem 4, our Superman problem. Superman leaps in front of Lois Lane to save her from a volley of bullets. In a 1-minute interval, there's our time, an automatic weapon fires 150 bullets, each of mass 8 grams. There's our mass at 400 meters per second, which is our speed. The bullets strike his muddy chest, which has an area of 0.750 meters squared. There's our area. Find the pressure on Superman's chest as the bullets bounce back after an elastic head-on collision. Well, in order to find the pressure, we understand that the pressure is force per unit area. In this problem, they gave us the area, but the issue is that we don't know the force of the bullets on his chest. So if we were to find that force, we would be able to calculate the pressure. How are we going to find the force? The elastic head-on collision part gives away that we're looking at a momentum, something to do with momentum. And just this is a reminder, we did this earlier this year. Here we have the mass of one bullet entering his chest, or coming in towards his chest rather, not really entering his chest, and then bounces off of his chest back to the left after a perfect elastic head-on collision. This, of course, means that there's no loss of kinetic energy and that momentum is also conserved. The reason we're talking about this is because this is a way for us to find the force by using the impulse momentum equation, the impulse momentum theorem. And that is that the impulse that acts on the bullets causes the bullets to have a change in momentum. The impulse is calculated by F times T. There's our connection to force, equals m delta v. In this case, the change in momentum is being caused by a change in direction of the velocity of the bullets. Further analysis, and the change is final minus initial. If we consider this to be the final state of the bullet leaving his chest, that would be v minus the initial velocity, which would be in the opposite direction, negative v. And here's the reminder that the change in momentum after a perfectly elastic head-on collision is actually twice the original momentum of the bullets themselves, or any object colliding elastically head-on. So F times T becomes 2mv. We now go ahead and we substitute. The event took place, the bullets all struck his chest in a minute interval. That's, of course, 60 seconds. 2, the bullet has a mass of 8 times 10 to the negative 3 kilograms, converting grams to kilograms. And there's 150 of those bullets that strike his chest in that 1 minute interval. So these two numbers together are what make up the mass of the bullets hitting his chest. They strike his chest at 400 meters per second. There's your velocity. Go ahead and solve for solve for F, and you get 16 newtons. We now go ahead and we solve for the pressure. 16 newtons divided by the area given to be 0.750 equals 21.3 pascals. Hopefully you paid good attention to the analysis of this problem, and hopefully you see a connection to it in a problem that we'll do tomorrow in class.